All right, well, we've talked a fair bit about statistics that we use to work with normal data and data that requires interval level, at the very least. So, and sometimes ordinal, depending on what research you're looking at and the types of data you have. But that's obviously not the only type of data we get. And in fact, a lot of data in psychology doesn't meet those criteria. So we have to have a way to analyze them. And one of the ways to analyze it, and one of the most useful ways, is actually Chisquare. And Chisquare is pretty cool because it allows you to analyze categorical data, right? Data that fits into only one category, like gender, pregnancy, voting, those types of things, right? So you're male or female or something else, other, or whatever you identify with. And then pregnancy, you're either pregnant, you're not. There's kind of no in between there. You can't be both, right? And voting is the same type of thing. You voted one way or you did not. So when we get data like that, if you recall, that categorical data, the only thing we can really do with it is look at the modes, right? So the modal distributions, and see what's the most common response. And there's not much you can do with the mode. I mean, you can't take an average of the mode. You can't take an average of all this stuff. It doesn't make any sense. So we have to have a way to analyze it. So sometimes we want to examine the relationship between some of these variables. So maybe gender and voting, or pregnancy and voting, or those types of things, or anything that's categorical that we want to essentially link to something else that's also categorical. Then we can do that using chi-square analysis. And chi-square is quite elegant. It's really straightforward, but it's elegant in what it does, and telling you whether or not that these distributions that you have observed are normal, or not normal, are expected or not. And we'll go ahead and look at those. So basically, let's look at the logic of this. First off, there's no mean to work with. There's no median to work with. We have no measure of central tendency other than the mode, right? This is because the values are arbitrary. I could say pregnancy, if you're pregnant, that equals a 1. If you're not pregnant, that equals a 0. Or I could say if you're pregnant, that's a 57. And if you're not pregnant, that's a 133. It doesn't matter what the number is there. It's just a placeholder in a sense. So the value that you give to these categorical variables is really irrelevant. And it's just something that the software uses to identify how many of these types of occurrences happened. And even new software doesn't even bother with numbers. You can just put in words and it goes from there. So so the numbers and the values here are completely arbitrary. The only thing that matters is how many of each, right? So we've got to work with that. So all we can do is look at that frequencies of occurrence. In a particular population, how many people are pregnant and voted Green Party? How many people are pregnant and voted Republican? How many people are pregnant and voted Democrat, or vice versa? You can flip that around. We can ask those types of questions, but all we can do is look at how many. So we have to go into a special type of non-parametric analysis, and I don't even like really calling it non-parametric because it's really about, it has nothing to do with the shape of the distribution, which is what parametric statistics and non-parametric statistics are about. It's about you use those in either a normal distribution or a non-normal distributed data, respectively. So in this case, we don't have any sort of distribution that we're looking at. It's there or not. It's like I've got 50 people in one category and 20 people in another, and so on and so forth. There's not much of a distribution going on. So it really isn't. I mean, it falls into the category of non-parametric statistics, but in reality, it kind of sits out there on its own and really is about categorical analysis. So, all right, let's look at an example here. All right, we got two categorical variables. And we're going to look at some fun here, pregnant and contraception. So are you pregnant, and did you use contraception? So we have two variables there that each have two levels each, right? Pregnant, yes and no. Contraception, yes and no. Okay. What is the chance that our observations are not due to chance? In other words, we're asking the question, was contraception effective? Because if contraception is effective, you should see something different than randomness here, right? Because if contraception wasn't effective, if it was just 50% effective and you're flipping a coin, then you should expect people to be pregnant and be on contraception at about the same rate as not pregnant and on contraception. So because we can't look at means, all we can do is look at those frequencies. So we need to find those expected values, right? So if everything is truly random, then we would have a really basic expected value. So what we're going to do is we're going to set up a contingency table, and then we're going to modify that contingency table a little bit based on expected distribution. So let's look at what actually happened here. So the made-up data, by the way. Okay. So our sample size is 300. You can see that down in the bottom right corner. Whoa. I love it when I hit the button. All right, there we go. Sample size is 300. And then what we have for the contraception question is, did you use contraception, yes or no? And you can add everything up and you can see how this all works. So every person in our sample answered both questions of contraception and or pregnant. So if you use contraception, then there was 20 people that said yes they used contraception and 130 people that said they did not. People that are pregnant, you had, let's see, what do we have here? People that said they were pregnant, there was 150, and I'm sorry, I looked at that wrong, so let me go over this again. Contraception, that people that used it, there's a total of 140 folks, and people that did not have contraception, did not use contraception, there was 160. Pregnancy, yes, so 150 people were pregnant, and no, 150 people. So that seems kind of odd, right? When you start looking at that, it's like, okay, well, maybe contraception did work, didn't work, who knows? It's an interesting sort of distribution the way this is set, or it's an interesting sort of set of results the way this it has been established. So we'll take a little bit closer look at it here, but what I want you to see first off is that these are the cells that we're going to work with, these 4 cells in the box. So yes and yes, so used contraception and pregnant, that's exactly what you would expect, very low, right? You wouldn't expect very many people to be in that category, based on what we know about contraception. But assuming we didn't know anything, we wouldn't have that expectation, right? So no and yes, no, I did not, no, I'm not pregnant, and yes, I did use contraception. So then we have a fairly high number, yes and no, so yes, pregnant, and no on contraception. So again, a fairly high number, and no, not pregnant, and no, not using contraception. So a fairly low number there as well. So remember what we talked about, we have to get expected values. If this was truly random, we have to worry about how many should we have seen in each one of these 4 boxes. So let's move on to the next slide here because it starts to cover that. So we look at what is expected in each cell. Now, at first you might think that we could just go, okay, we have 300 divided by 4, right? So that gets you 1 in each box. That gets you your answer for each box. So that would be what, 75? But that's incorrect. We can't do it that way because the proportions are not correct. So let's look at how that proportions is set up here. There's a different number of people in each condition, right? So in the contraception condition, there was contraception yes, there was 140 people, and contraception no, there was 160 people. Now it just so happened that the pregnancy conditions, it was split down the middle, so we can kind of leave that alone for now. But because of those different numbers of people, we can't just, in each contraception category, we can't just divide n by 4 and fill each one of those expected values and then compare our observed values to those expected values. We just can't do that. So what we need to do is take into account the exact proportion of people that fall into each category, right? So we're going to take the row total and multiply it by the column total and divide it by n. So what we're ultimately going to have there is, when we do that, that'll get us our expected distribution. So the row total, for example, for the contraception yes was 140. The column total for contraception yes was 150. So we would multiply those out and divide that by 300. That gives you your proportion that you would expect in each one of those cells, and so on and so forth. And we're just going to continue that for each and every one. The chi-square itself is where we're going to take what we actually observed, and subtract that expected, so the model, right? So we're going to take what we observed and subtract that model, square it, and divide by the model number again, right? And then we're going to sum all those things up. That is actually the statistic, right? So let's work an example here. So again, then as usual, we go to a table and look up whether or not that statistic is significant, given our degrees of freedom and sample size. Then when it is significant, we're saying that this was not an expected distribution. This was a distribution that was something other than random, because if it was random and there was no effective contraception was not effective, then we would say no, we would say that if it was not effective, if contraception was not effective, and we got a distribution that matched our expected distributions, right? Then we would say it's not significant. But if it is significant, then we're really saying that, hey, there's something that's driving a difference here beyond randomness. So people didn't just get randomly tossed into those categories of contraception or pregnancy. So with we worry about this degrees of freedom because, again, that's going to talk about how many scores are free to vary and things like that, and we use that when we calculate whether or not it's going to be significant. So keep in mind that you can have more than 2 categories here. You can have a 3x2 analysis, a 4x4 analysis, that type of thing. So it's just, it gets a little complex to present, so I'm just presenting it as a 2x2, but your book does talk about how you go into more detail with more complex stuff. So let's just go ahead and flip through the sample here, and remember, we're going to just do this. We're going to create the expected distributions first, and then we're going to create then we're going to take that what we actually observed and subtract it from the expected, and then, or take observed and then subtract the expected from that, square that and divide it by the subtracted again, and then sum all those things together, and then we'll get our chi-square statistics. So let's go ahead and look at it. So chi-square equals 20 minus 70 squared divided by 70. It's like, well, where in the world did all that come from, right? Excuse me. Well, if we look at the model, remember the observed score was actually 20. Actually, I'm just going to zip ahead here a little bit so we can walk through this. So the observed score was actually 20, 20 minus 70, right? So how did we get 70? 70 was that row total times column total divided by n. So if you take, so we've got, what do we have? For the contraception yes and the pregnancy yes cell, we're going to take the row total, okay, which is 140, multiply it by 150, and divide that by 300, and the end result is 70. For the pregnancy yes and the contraception no condition, we're going to take 160, multiply it by 150, and divide that by 300, the answer is 80. So you can see that those are expected distributions. So the model itself expects a distribution, if it was truly random, 70 people in the yes and yes condition and 70 people in the yes no condition, or sorry, 80 people in the yes no condition. And then we continue that process. We say for the no yes condition we have 70 we would expect, and the yes, the no was 80. And normally it's not this clean. Normally you get really weird stuff in here, but it just so happened that the way I did the math, and I just picked numbers out of my head and it came out this clean, which is kind of lucky. But so we're going to do all that math. So we're going to take 20, all right? So now we're going to move on to that second formula that was observed earlier, or that we looked at earlier. We're going to take the, we're going to work that first cell in the top left corner there. We're going to go 20 minus 70 and then square that, all right? And then divide that whole thing by 70, and the end result is 35.71. We get that twice because you have the same thing in the no yes condition there right next to it, and then we have 31.25 twice because we have the 130 and all that stuff. So anyway, the end result is that we have all of we have all these things here for our chi-square. So we're going to go 35.71, 35.71, 31 and a quarter, 31 and a quarter, which equals 133.92 divided by 2 degrees of freedom. So the question is that significant or not? And the answer is, in this particular case, yes, it is significant. So we now know that contraception and pregnancy are related in some way. There's some sort of non-random distribution with this particular data set. So that's essentially chi-square, and chi-square is a very useful statistic. You'll see it a lot, and as a side note, sort of a Jeopardy question, a chi-square distribution, which is a normal distribution, basically matches matches the distributions for t-tests and ANOVAs as well. So it's a very common thing. It should be used more often than it is, believe it or not, but I think it's probably the most commonly used non-parametric statistic out there. It's the one that's most understood by folks that tend to do statistics. So let's look at some of the assumptions that are associated with this. Right off the bat, there's no repeated measures. You cannot have multiple people in multiple categories. You can't measure people multiple times because it tends to throw off some autocorrelation stuff, and the end result is that those cells need to absolutely be independent of each other in order for the assumptions of the statistic to work. And another weird one is that expected frequencies should be greater than 5. If you end up with a cell where the expected frequency is 5 or less, then it basically tells you the statistic is completely uninterpretable. And I've done quite a bit of analysis with chi-square, looking at whether or not people have used online technologies in a class and whether or not they like that, essentially. And I ran into this a lot because of how many people that wouldn't have used a technology or would have used a technology. So like everybody's used PowerPoint, so there was only 1 or 2 people that would have not used PowerPoint in a particular class. So as a result, it was impossible to finish the analysis. It was just, there's nothing you could do. But on several of the statistics, there are several of the questions like, have you used game type technologies in a classroom or something like that, then I was able to get those appropriate distributions that way, or the expected frequencies. So that it is a limitation, and it really buggered some of my analysis. It bit me in the bum a couple of times, but it's basically because of the type of questions that I was asking. So ultimately, conclusion here: if you want to have if you do have categorical data, you wanting to see if those things are by chance or not, then use the chi-square analysis. It's a useful little statistic. So, and when you read about it, just know that it's asking that question of: are these differences due to randomness? Is this distributed in a way? Are these frequencies, these cell frequencies, are they random or are they not? And if they're not, then we say it's significant. Okay, talk to you soon. Bye.